Hello everyone, welcome again to another episode of Aerospace Engineering with Brian McNulty. Today I'm going to be deviating from our usual program and I'm going to be talking about some fundamental physics that are necessary for the aerospace engineering program. So I'm just going to start out with the basics and then we'll just take steps to get to the more advanced concepts from here. Without further ado, let's get started. So there are four different characteristics that we will go into when describing motion. Motion is going to be one of the most fundamental concepts that we talk about in physics. Now, the four characteristics that describe the motion are going to be time, position, velocity, and acceleration. It's important to note the units for each of these four characteristics of motion. So time is going to be measured in seconds. The symbolic representation of that is going to be S. Position is in meters, and that's M. Velocity is going to be measured in meters per second. So that's in the units meters divided by seconds. And then acceleration is going to be measured in meters per second squared. And the symbolic representation for that is meters divided by the square seconds. Now that we've seen the units for each of the four characteristics that we'll be using to describe motion, we'll now take a look at how they are all related to each other. Okay, so what we have here is the same table we saw before, except you can see on the left I've added some symbols in red. The triangle, it's a delta symbol, capital delta, and it essentially in mathematics means change in. So, as you can see, the one associated with time is the change in time. The one associated with position is delta x, so change in x. Now you can see something interesting happen here. For velocity, we're using both of those, and it's delta x divided by delta t, which just means the change in position over the change in time. And you can see something similar is happening with acceleration. It's just the change in velocity over the change in time. So some of you may be versed in calculus, and so I thought that I would take this time right now to show you the symbolic representation of these characteristics of motion as they are described in that field. So I've once again added to our table, and as you can see on the left column, what I have written is just the symbols for calculus. Notice velocity, that dx over dt, that turns out to be the derivative of the position function. So when you express these things in terms of t, you get an equation, and a position, if you can differentiate it, you get the velocity, and if that function that you get, which is now the velocity function, is differentiated, acceleration results, the acceleration equation results. So just like I was saying before, except now I'm going to talk in terms of calculus, essentially velocity is the derivative of the position vector, and acceleration is the derivative of the velocity vector. Now, you might be wondering, what if I want to go from the velocity vector to the position vector, or the acceleration vector to the velocity vector? Essentially, do I want to go backwards? Well, those of you who know calculus know that there's a simple tool for that, and we call it integration. Okay, so now you can see I've changed our table a little bit from the last time we looked at it. And these little symbols here indicate that we are looking at integrals, these long S-looking symbols. Now, when you express motion as a function of time, you can look at the position function, which is going to be the x of t. And you'll notice that if you integrate the velocity function, that's what gives you the position function. Similarly, if you integrate the acceleration function, it gives you the velocity function with respect to time, that is, time t. Okay, so we've gone through the symbolic representations of these four characteristics of motion. Now I think it will be helpful to look at some graphical representations of these functions as functions of time. So let's check it out. Okay, so you can see I have two graphs drawn here. Let's take a look at this one on the left. You can see that this is a position graph because on the y-axis it says x of t. That means change in position, and over time is on the x-axis. You can see that in red I have drawn the curve of the average velocity. It just happens to be the secant line that connects x of t sub 0 and x of t sub 1 on the graph. And you can see there's an area under this curve, but it's not a very good approximation. So this just gives the average velocity, that secant line. And the blue curve is not linear. That is an indication that the velocity is changing. And so I've drawn these arrows down here to kind of represent over time what is happening. So we can see that the black dots are getting farther and farther apart. That means those represent the position. And the arrows getting larger represent an increase in velocity. Now, you can see that, and we're going to visit an earlier concept that we talked about in this video, that in fact the velocity vector is the derivative of x with respect to time. So if we look at this graph on the right here, we can see that that is definitely the case. As the final time minus the initial time goes to 0, in other words, as those 2 points get closer and closer together, we get almost a perfect approximation for the instantaneous velocity, which is just the exact velocity at any point on this position graph. So in this graph we have a velocity over time graph, and so this is going to be representing the function v of t. And what's happening here in the first half on the left of the blue line is that the velocity is increasing, and it looks like that's a linear thing, so that means that it's increasing at a constant rate. You notice if we take the derivative of any linear line, we just get the slope. And that just turns out to be what the acceleration is. So any point along this line where it's increasing, the slope is equal to the acceleration vector. And to the right, the same goes, except this is a straight line. This means that the velocity stopped changing. This means this could be representative, let's say a car from stop decided to accelerate for 3.5 seconds, according to this graph. And then it stayed a constant speed after that 3.5 seconds. And so the derivative of this right side right here, well, that's just a constant. That could be represented as just v of t equals 3. And the derivative of any constant is 0. So, and that's also the slope of the graph at that point. So that means that on the right of this blue line, the acceleration would be 0 because the slope of the velocity graph is 0 at those points. You're probably wondering, where are all the equations, man? You know, we've just been looking at graphs and explaining these abstract concepts about the relationship between these four characteristics of motion. Well, yeah, there are equations, and we're going to look at them right now. They are known as the kinematic equations. And so we're going to first take a look at the equations that you can use when the object that you are analyzing is under constant acceleration. So here I have written down the kinematic equations of constant acceleration. There are a couple more that we'll look at, but for right now we're just looking at constant acceleration. That's very important to remember. So at the top we have x of t, which we discussed is the position function with respect to time, and it's just going to be 1/2 at squared, where a is the acceleration, plus initial velocity times time plus the initial position. So if you are starting at, let's take notice of this, if you're starting at position 0, this initial position just goes away and you can cancel that x right out of there, leaving you with only 2 terms being added in the equation. If your initial velocity is 0, in other words, if you're starting from rest, then the formula just simply becomes 1/2 at squared. So if I just cross those out so you can see what I'm talking about, if you're starting at position 0, that can go to 0, which means it disappears. If your initial velocity is 0, well, that just takes care of that term. And so this equation, x of t equals 1/2 at squared, is what you'll be left with. And that essentially is saying that you're starting at position 0 with an initial velocity of 0. Now, on to the next one, the velocity function. We discussed before that that's just the derivative of the x with respect to t. And if we take the derivative quickly using the power rule, we can see that it just comes out to be at plus v naught. Now, again, if your initial velocity is 0, in other words, you're starting from rest, this term just goes away to 0, and you simply have velocity equals the acceleration of the object times the time that it is accelerating. That will give you the velocity at the point time t. Now to the next one. This one's acceleration, and as we discussed before, that's just the derivative of the velocity function with respect to t. Now, as you can see, by taking the derivative of this one using the power rule, we simply just get a acceleration. No matter what t is, acceleration is always going to be constant. Now, if acceleration is constant, it does not depend on the velocity function or the position function. That's very important. So remember that. This is for constant acceleration. So here are 4 other equations. I mean, they're basically the same thing. They're just rewritten for different purposes. So this top left one here, d equals 1/2 gt squared. You can use this one when your initial velocity is 0. So basically, if you're falling from rest or starting from rest with a constant acceleration. And then this one is just another way to write distance. It's just the average velocity times time. It's probably the most simple one. This one I like to call the 2AD formula, and that's just how it goes. You use this one if you aren't given the time. So if the problem says nothing about time, this is a good starting place. And then this final 4th one here, that's just saying the final velocity is if you have an initial velocity plus the acceleration times time. So you use this one if you have an initial starting velocity other than 0. All right, so I think this whole lesson has been great. I think that now we need to do a problem to kind of give an example of what situation these types of things will be used in. So let's check it out. A rock is dropped from a 500-meter tall building on Mars where the gravity is 4 meters per second squared. How long does it take to land? What is the speed of the rock just before it hits the ground? Now, take a moment to pause the video right now before you look at the solution, and I'll work it out. Okay, so hopefully you guys have had a look at the problem and gave it a shot. Now, here is what I did. There's probably more than one way to solve this, but this is the first thing that came to mind. So it looks like I wanted to solve for the speed just before it hits the ground first, even though in the question I asked for time first, but in this case you could do it either way. So notice that it doesn't say anything about time in the question. So if you remember what I said about that, we're going to use that 2AD formula, and rearranging it for final velocity gives this square root of 2AD. That equals the final velocity. And so A is just going to be the acceleration of gravity on Mars, which happens to be 4 meters per second squared. And then D is obviously going to be the distance it falls from rest, might I add, which is going to be 500 meters. You plug that into a calculator and you end up with a final velocity of 63 meters per second. Now, so the second part is going to be the distance. And, well, we're going to use the distance formula, which equals 1/2 AT squared. If you look at this formula, that implies that t equals the square root of 2d divided by a. And d again is going to be 500, and a is the acceleration of gravity on Mars, which is 4 meters per second. Plugging that into your calculator gives you about roughly 16 seconds the object was falling for. And that's how you use the kinematic equations. Okay, so in this video, we talked about the 4 characteristics of motion, how we describe them symbolically as well as graphically. We looked at the different graphs of position, velocity, and acceleration with respect to time, and we interpreted that into the world of calculus, which was pretty exciting. And then we took a look at the kinematic equations and different ways that they can be manipulated to get you the information that you're looking for regarding any of these 4 characteristics of motion. I hope you enjoyed the video. Don't forget to like and subscribe, and I'll see you next time on another episode of Aerospace Engineering with Brian McNulty.